Hello and welcome to my video report of Lab 1, an object moving with constant velocity. In this lab, we had to record an object moving at constant velocity, analyse the object's motion in Tracker, create a model to simulate the motion, and compare the simulated data and experimental data. So first we had to record the object's motion. For this lab, I recorded a basketball moving along a flat surface, and I recorded the properties of the basketball here. We can watch that video now. Next, using Tracker, I recorded the center of mass of the basketball to obtain the observed positional data. I used the diameter of the basketball to set the scale, and we can watch that video now. Then we had to obtain the initial conditions to create our model, and the mass we recorded earlier, the velocity was worked out by taking the displacement of the first two data points and dividing by the time elapsed between those two. And that gave us a velocity of 1.236 meters per second. Using Newton's second law, we know that an object moving at constant velocity has a net force of 0 newtons, and the initial position of the basketball was slightly off the origin that I used, so this is displacement from the origin. So in creating the computational model, we had to set the initial conditions, and these are the lines of code that do that. To update the velocity and position of the ball, during each iteration of the loop, we have to calculate the new velocity and the new position. However, considering the net force in this situation is 0, the velocity remains the same, hence the constant velocity, and the position of the ball is just that velocity times by the delta t. So next we're going to talk about the assumptions made in the model. Both friction and air resistance are ignored for the simplicity of the model. But obviously in real life, both of these forces affect the basketball and it would eventually slow down, whereas in the model it would keep going with that same constant velocity forever. And the model ball also only moves in the x direction, whereas in the video we saw that the ball moved towards the camera slightly as it moved away from that center line on the table. Also in the recorded data, we know that the y position of the ball changes as the table wasn't quite level. But this isn't accounted for in the model, and it may affect our results later. So these are the results of the simulation. We can see that the ball begins slightly displaced from the origin and moves in the positive x direction. And then the position time graph on the right shows that it moves with a constant velocity. Now to compare the data. On the graph on the right, we have a position time graph with both the model and experimental data plotted on it. The experimental data is in red and the model data is the blue line underneath. We can see that at the beginning, the two line up really well, and then at about the 0.6 second mark, the experimental data begins to be slightly less than the model data. This could be for a number of reasons, but as we discussed earlier, in the real world, the ball experiences forces that aren't modeled in the simulation. So the friction and air resistance will eventually slow that ball down. But another thing we saw that in the video of the ball rolling was that it moved away from the center of the table, away from that line, towards the camera. So the fact that it's also moving in the z direction means that it's moving less in the x direction. So that probably affects it as well. To round out Lab 1, we were also asked to answer a couple of questions about the experiment we just performed. The first of those is what would happen if we were to reverse the orientation of the axes. Now, in my model, the ball moves in the positive x direction. If you were to reverse this, it would be moving in the negative x direction. Now, this would make all the positive displacements from our output negative. So we would see on the position time graph that the line would reflect over the x-axis. Yeah. So the second question asks if we are capable of working out what forces constitute the net zero force on our ball. Now, as we know the ball is moving with constant motion, we know there is zero net force from Newton's second law, but unfortunately it doesn't tell us what components add up to a net force of 0. We just know that there is no overall force. So unfortunately we aren't able to decipher the individual forces acting on the ball. We just know that their total is 0. Thank you very much for listening.